What is up, multivariate gang? Today we are going to be talking about a vector operation called the dot product. I think this video might be a little bit long, so let's just get right into it. Alright, definition of the dot product. The dot product is a form of vector multiplication. It's written v dot u, that little dot. That's why it's called a dot product. You guys remember multiplication symbols? You would have a dot b, which was the same as like a with the cross symbol b, which is same as a, b in parentheses. Those notations don't hold up for vectors. The dot, the cross, those two mean their own things, and this isn't a thing for vectors. So keep that in mind. All right, so v dot u. V dot u is a scalar quantity. The dot product is a scalar. That is very important. The dot product is a scalar. The dot product is equal to Vx Ux plus Vy Uy plus Vz Uz if it's in three-dimensional space plus V whatever U whatever dot for however many dimensions you're working with. Of course, we're going to just be working in three spaces, so this will be all we've got to worry about. All right. Example problem. Find v dot u if v is 147 and u is -2, 5, -1. Okay, so we just learned that all we do is we multiply these two components, multiply these two components, multiply these two components. Easy peasy. So v dot u equals -2, or here, let's go and do it. 1 times -2 plus 4 times 5 plus 7 times -1, which is equal to -2 plus 20 minus 7, which is equal to 11. All right. And it's just 11. It's just a normal number. Just the number 11. Nothing special. Okay. Continue. Properties of the dot product. The dot product the dot product as an operation, not necessarily the number itself. We'll talk about that in a second. But u dot v equals v dot u. The dot product is commutative. And that makes sense. You can prove that to yourself fairly easily. I'm going to omit all proofs to make this video a little bit shorter. U dot v plus w equals u dot v plus u dot w. That is another way of saying the dot product is distributive. K times u dot v equals ku dot v equals u dot kv. That is another way of saying that scalar multiplication is commutative with the dot product. Or I guess not commutative, is associative with the dot product. Doesn't matter if you multiply the scalar by the actual dot product or the scalar by either of the vectors, you will get the exact same number at the end. All right, v dot v equals the norm of v squared. It's pretty straightforward. V dot v equals vx plus vy plus vz. I know I said I would omit proofs, but I think this one is easy enough. So v dot v equals vx squared plus vy squared plus vz squared, which we know is the norm of v squared, three-dimensional Pythagorean theorem. And v dot the zero vector, or the zero vector dot v, is the number 0, not the zero vector. Zero vector dot non-zero vector equals the number 0, which makes sense because you're multiplying. Because the zero vector has components of 0, 0, 0, 0, 0, all the way to infinity, no matter how many dimensions you're in. So your dot product is always going to equal 0. Easy enough. All right. Uses of the dot product. Seems like we kind of just made this thing up, and we did, but it is a very useful tool. For starters, you've got physics. It has two really big uses in physics. One of them you've probably already encountered. The work done on an object, which is equal to the energy put into an object or taken out of an object. Like if you've got a block and you're pushing the block with a horizontal force, and the block is going up, is being displaced in this direction. The work done on the block, the work is a scalar quantity that is equal to the dot product between the force and the distance. Which is cool. And also magnetic flux, which is something that you guys haven't really talked about, but you have if you have some area and you have magnetic field lines flowing through it, flux is equal to the dot product between the field lines. And I frankly can't remember the variables, so I'm not going to waste your time trying to remember them. Dot the area vector, and the area vector has a magnitude equal to the area, and it's points normal to its direction is normal to the surface. That's not important. You guys don't. You might be asked some questions about this one. You guys probably already know that one. So, but what the dot product is used for, like in math, is to find the angle between two vectors. Now, how do we do that? Now, v dot u equals vx plus, and we'll keep this in 2 space for now, just to make it a little bit simpler, but the same holds for 3 space. Vxux plus vyuy. And that's also equal to the norm of v times the norm of u times the cosine of theta, where theta is the angle between the vectors. Now that I am absolutely going to prove to you, because it's not intuitive at all, but incredibly important. So let's go and show that. Proof. All right. And this proof is like straight out of the book, guys. Like it's in there. You can ask Mr. Goff for it. He probably doesn't have it like memorized or anything, but you can figure it out. All right. So you've got vectors u. You got vector v and vector u, and you've got some vector from the head of v, head of u. Actually, let's go the other way. From head of the second to the head of the first, that's v minus u. Cool. All right. And we've got this angle between them, theta. All right. We know that the norm of v minus u squared equals the norm of v squared plus the norm of u squared minus 2 times the norm of u times the norm of v times the cosine of theta. And that's law of cosines. That's just straight law of cosines. All right. Now, we know that this junk right here, we know that the norm of v minus u squared is the same as v minus u dot v minus u. Because of that property right there. All right. And we know that the dot product is distributive. So all this mess is equal to v minus u dot v minus v minus u dot u. I distributed this across this. I foiled it, kind of. All right. And so if we actually go ahead and distribute these, multiply those out, we get the norm of v squared, that's just v dot v, minus u dot v minus u dot v minus, or oh no, plus, because that's negative and that's negative, plus the norm of u squared. And we know that all that mass is equal to norm of u squared plus norm of u squared minus 2 norm of u norm of v cosine theta. And if I forget the fish hooks, guys, sorry, it's my bad. All right, we've got a v squared on this side and a v squared on this side. We can cancel those out. We've got a u squared on this side and we've got a u squared on this side, so we can cancel those out too. So that leaves us with negative 2 u dot v as equal to negative 2 norm of u times the norm of v times the cosine of theta, and get rid of the negative 2 on both sides, and we are left with our end results. U dot v equals the norm of u times the norm of v times the cosine of theta, which, if we were interested in the angle between these two vectors, we would simply solve for the cosine of theta, and we would get cosine theta equals norm of u times the norm of v all over u dot v. Boom, boom. Thus it is proven. Good stuff. All right. Example 2. Find the angle between v and u if v equals 1, 4, 7 and u equals negative 2, 5, negative 1. All right. So we know cosine theta equals v dot u over norm of v times norm of u. All right, so v dot u is 1 times negative 2. Those two multiply together, plus 4 times 5. Wait. Whoops, I did you guys wrong. This is not true. This is not true at all. There we go. U dot v all over There we go. Sorry, guys. Hope that's not super confusing. My bad. All right, back down here. Plus 7 times -1. That's just multiplying these two. Those two. All right, times square root of 1 squared plus 4 squared plus 7 squared times the square root of -2 squared plus 5 squared plus -1 squared. All right. Some easy math. We already know that this top part is 11 because we solved for the dot product in an earlier example. This down here, that's 1 plus 16 plus 49, so that's the square root of 56. And that's 4 plus 25 plus 1, so that's the square root of 30. And we can simplify that a little bit before we have to multiply those together. So that's 1 over 2 times the square root of 14 times the square root of 30. It's equal to 11 over 2. Oh, and there's a 2 in there and 2 in there, so we can bring those out too. So that's 4. Here, I'll put them together and then take them apart again. So that's square root of 420, which is equal to 11 over then 420. Divide that by 4, we get 105, and that's 3 times 5 times 7. So there's nothing else in that, but we can take that out. So we get 4 times the square root of 105. Boom. All right, cosine theta equals 11 over 4 square roots of 105. So we got to plug theta equals cosine inverse of all that stuff, all that jazz. And we get, let me grab my calculator. And we'll go ahead and do it in degrees. That gives us 74.4326 degrees. All right, easy enough. Now, without doing this whole calculation, we can glean some stuff about the sign of the dot product just by looking at about the angle between the two vectors just by looking at the sign of the dot product. All right, so we know that the dot product is equal to, we'll call them vectors A and B. A, B, just to get used to you guys calling them different things. AB cosine theta. Cool. All right, so we know this is always positive, and this is always positive. So we know if this is greater than 0, if the dot product is positive, then we know that theta has to be greater, or theta has to be less than pi over 2, or 90 degrees. How do we know that? Because cosine is only positive when theta is less than pi over 2. And if these guys are always positive, the only way that this whole thing can be positive is if cosine theta is positive. We know that if all that is less than 0, that means theta is greater than pi over 2. That means that our vectors look something like this. Got an obtuse angle. And if the dot product is equal to 0, means that theta equals pi over 2. Because that would mean cosine of theta equals 0. All right, So if dot product's positive, cosine's positive, angle is less than 90 degrees or pi over 2. Dot product's negative, cosine's negative, which means that angle is greater than pi over 2 or 90 degrees. Dot product is 0, cosine theta is 0, which means that theta is pi over 2. Alright, hopefully this didn't run too long. I will see you in the next video as we further explore the dot.